You're still eating. Where did you get the pizza from? Oh, I saw the sign for that. Oh well.
There wasn't that many people there, but I had eaten after I ate at the Casey Grill. I was like, I feel like I had free food. I still got free food.
Today I brought my lunch. I remembered my lunch today, so I ain't gonna be hanging.
Good for you.
Good job. There you are. I was waiting for you. Not really, just a little bit. It's cool. You're fine. You're fine. Okay. Oh shoot, I got new chapter 13 stuff. So here we go. Chapter 13. New chapter. This is over that word that we have been saying for the last couple of days. Equilibrium. This chapter, we're going to learn the fundamentals of equilibrium. Next two chapters are more details, more specific types of equilibrium. This is just fundamentals. So these are the lecture 8 slides. Okay. And very first section is I know we've been talking about this, but let's just get down what exactly is equilibrium. So when we're talking about chemical equilibrium, right? Because of course this is chemistry class, and we're looking at chemical reactions, right? I want you to know, right? Okay. Some chemical reactions are what we would call irreversible, okay? Some reactions are irreversible. What does that mean, do you think? They cannot be undone. They cannot be undone. You can never take the products back to their reactant form in any way at all, period. Easy example, something that's irreversible. When you cook an egg, can you ever take that cooked egg back to its raw form?
No.
Never. Irreversible. Okay. But most reactions are reversible. You can take the product that forms and turn it back into reactant. Most chemical reactions actually are this way. Now, it could be easy to do this, or it could be very difficult to do it, like water. Think about water, right? If I put water together, what am I putting together? H2 and O2. Okay. Guys, that happens very easily, readily, quickly. Okay, that happens, right? But don't we know that we can take that water and break it back apart? That's what electrolysis is. Did we talk about that in my other class in Chem 1? Maybe not. Okay. But we can decompose water. We can take water and break it apart. We have to apply a lot of, you okay? We have to apply a lot of energy to make that happen, but we can do it. It is reversible. That process, that reaction is reversible. What we want to look at is when we have one of those reversible reactions, which is most reactions, okay? When we have a reversible reaction, we are going to represent this reaction as an equilibrium. These reversible reactions, we're going to now be writing them as an equilibrium reaction, which just means we use what kind of arrow? The double arrow. Irreversible or no equilibrium has what kind of arrow? Just the one arrow that we've been used to writing, okay? But now what I'm telling you guys is even though we were writing a single arrow, pretty much every reaction we've looked at, Gen Chem 1 and this class, have actually really been reversible. There's been an equilibrium the whole time. For example, here's this compound. It turns into, it actually splits, right? Splits, breaks itself in half. Okay, it turns into two of these. This is an equilibrium. So we use that double arrow. That's what we're going to see from now on is the double arrow, meaning equilibrium. And what does it mean now to be at equilibrium? What's the best way to define what it means to be at equilibrium? And that's the key word. Equilibrium means the rate, and we would talk about this direction being the forward, right? And we would talk about this direction being the reverse. At equilibrium, the rates are equal. Okay. So what does that mean? It's not necessarily true. It is not the same concentration value on both sides. You guys know right when we just read the square brackets, right? Concentration. Yes. But what is true, but what is true, okay, when the reaction has reached equilibrium, what is true, the rates are equal and the concentrations are constant. At equilibrium, this has a constant concentration. This, at equilibrium, has a constant concentration. They're not necessarily the same, but they're constant. They're unchanging. Let's add that. And we have constant concentrations. Okay. If we look at these two diagrams, this is illustrating what I just said about what is equilibrium. Equilibrium is when the rates are the same. That's this bottom image. At equilibrium, the rate forward and the rate in reverse, same rate, okay? At equilibrium, the concentrations are constant. Not necessarily the same, not equal, but just constant and unchanging. However, we can do things to change the concentrations, can't we? We can physically add more of something. We can physically take something out, right? What's going to happen to the equilibrium if I mess with it? Okay, let's make sure we understand. Well, by messing with it, right? These equilibriums are, I've said this word before too, dynamic. What does that mean? Not static. It can change. The equilibrium can change. What the word that we're going to use is the equilibrium can shift. Okay, a reaction can shift to get back to equilibrium. Right? We can change the equilibrium. Okay. So not this, I got to talk about one. So the third section is where I'm going to talk more about these changes. Okay. Now, the second, so we define what is an equilibrium. Rate equals, concentrations are constant. Let's talk about how we define or calculate, how we mathematically talk about equilibrium. Okay. So this is all just words, really. Okay. So about the math of it. So this is the type of symbols that we're going to use in equilibrium concentration calculations. Okay, so we're going to look at some symbols that describe equilibrium. First one, so when we have a reaction, we can look at something called the reaction quotient, which is a capital Q symbol. Okay, a reaction quotient. This is something we can look at. This is going to be a math expression. If I'm talking about a quotient, what does that mean in math? The answer to a division problem. I'm going to be dividing. Okay. A math expression that compares or divides products. This is the generic way to just remember this. Products divided by reactants. Okay. But what about the products? And what about the reactants? What are the things that I'm actually going to be dividing? What are the numbers that I'm going to divide? I am indeed going to be looking at the concentrations. So if I'm using concentrations, what is the symbol that we use for concentrations? Yeah, because this is molarity concentrations only, you guys. None of those other kinds of concentrations. No molality, no percent by mass, just molarity. Now, the other thing that we can use, and we're going to see this too, is if our reactants and products are gases, we could also judge their concentration by looking at their pressure. You can look at pressures for gases. What units of pressure? Actually, whatever units you want to use. We could use atmospheres, we could use torr, we could use kilopascals, just pressure, okay? Here's what we got to remember, though. Can you see, Veronica? Here's what we got to remember. When we write this quotient, we have to take into account how many moles of that element there are, which means we got to look at what from the balanced equation. If I have to think about how many moles, I got to look at the coefficients in my balanced equation. Okay. So let's say we have this generic reaction, okay? A and B make, oop, wrong arrow, right? double arrow. Make C and D. Okay. If I have to think about the amount that I have, those coefficients are now superscripts. They're exponents of the concentration. See how that is written? Your coefficients are the powers that you raise the concentrations to. Okay? And notice always what is on the top. Your products. And how are these products combined on the top? They are multiplied by each other, divided by your reactants raised to their exponents times each other, right? What if I have pressures and not molarities? Okay, P is our symbol for pressure. We're taking the pressure of that, but I still have to raise it to its exponent. It is still raised to the power of the coefficient from the equation. Okay. So we might sometimes see after our Q or other symbols that we're going to see, we might write maybe specifically a little C, meaning I'm looking at the concentrations. Okay. Or if I'm looking at pressures, I might write QP. Okay.
Isn't it products divided by reactants?
Yeah. Excuse me. Products. Thank you, Loretta. Okay. We're going to see a way to relate these two values. If we can do both concentration and pressure values, there's a way to relate those two Q's. Okay, we'll see that. All right. What is never, there are some reactants or products that will never be included in your expression, okay? There's some that will never be included. And it has to do with what phase they're in. What kind of things have a concentration? What phase? Solids and liquids do not have concentration. Solids and liquids are pure, right? Are they a mixture? Concentration only applies to mixtures, doesn't it? Aqueous or any kind of solution. We see aqueous the most, but anything that's a solution. So we will only include in our expressions anything that is a solution. So again, we're most used to seeing aqueous as the phase, or anything that is a gas, right? So what will you never see? What will we never write in our Q expression?
Pure solids.
Pure solids, pure liquids. Never.
One question.
Yep.
This might be not related at all, but in JQ1, when we wanted to write a complete ionic equation, we wouldn't separate aqueous. Is it related to that?
It's kind of the same thinking. Why would you try to split in an ionic equation something that is not made of ions, right? Here, how can you possibly talk about the concentration of something that has no concentration. Liquids and solids don't have concentrations, right? Or how can you talk about pressure of a liquid? Liquids don't have pressure, right? Solids don't have pressure because it's not at all applicable to the things we're looking at. Like those didn't have ions in them. That's why you don't include them. Practice writing one. Look on your brand new in class, chapter 13. Can you write what both the QC and the QP expressions would look like for this very first equation? Okay. A, is it an equilibrium? Yes, I see the double arrow. If it's an equilibrium, we can calculate this thing called the reaction quotient. How do we calculate that? What does that expression look like? Remember, you have to write products over reactants, and you have to raise those concentrations or those pressures to the power of its coefficient. I only have one product here, right? If I'm doing the concentration expression, that's SO3. And then what? To the second power squared, because there's a 2 coefficient. That's the only product. So now divided by on the bottom, I have SO2 raised to the second, and I have just oxygen raised to the first, right? What would the QP look like? Identical, except instead of writing brackets for molarity, I'm just writing P for pressure. P squared. P of what? That gas, SO3. Bottom, P squared. I'm at SO2 pressure times the pressure of O2. Very straightforward. Yes? Yes. Okay. Something important to know about Q is this reaction quotient can be calculated at any point of the reaction. At any moment in time of the reaction, I can calculate Q. I can compare products to reactants. At any moment in time, I can calculate the quotient. If I have the numbers to plug in, I can calculate. So let's just remember, Q can be calculated at any point. Because why am I comparing these concentrations or these pressures anyway? Why am I comparing them? What do I know to be true when the reaction is at equilibrium? They're going to be constant concentrations, right? And if they're constant, and I compare them when they're constant, what am I going to get as an answer? Another number that's also constant, right? Right? Is Q constant? Q is whatever it is at that moment in time, right? Q is not a what? A constant value. But there is a value for an equilibrium that is constant. It's when it's at equilibrium, right? It's when it has reached equilibrium, there is a constant value. And that is called K, capital K. Not little k. So many K's. There's also so many C's. There's a ton of C's and K's in chemistry. It's like, why couldn't you come up with a different letter? No different letter. Okay. When we have reached equilibrium and we are calculating a quotient, at equilibrium, that quotient is now a constant number. At equilibrium, there's a constant value. and that is known as the equilibrium constant, capital K. Equilibrium constant K. Notice that the format of writing K is identical to how we wrote Q. Y'all see that? It's still what? Products over reactants. It's still those raised to their coefficient, right? It's just that now K would be a constant value for that reaction. K is a known constant value for many reactions. But K is only found when what is true? The reaction must actually be at the state of equilibrium, which means what? Equal rates and constant, that was kind of hard to say. Hang on. Constant concentrations. There we go. So can I calculate K values based on concentration? Absolutely. Can I calculate K values based on pressure? Absolutely. Just like if I'm just talking about concentrations, again, you might see me specifically put a C there for concentration. If I'm talking about pressures, you might see me specifically write a P, right? Same thing. All right, let's see. Look at number 2. I got a mixture of gases and 0.1 moles of NO2. Now look at the equation, the way this equation is written. I need to come back. I want to do this example, but then I need to come back to this screen, so y'all don't let me forget to talk about these words, okay? Okay, but let's do this example first. Okay. So before the reaction gets going, okay, I'm adding 0.1 moles of NO2 to a 1 liter flask. What is NO2? There it is right there. That's my, what, reactant or product? That's my reactant, okay? And then the concentration changes, blah, 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 blah. Okay, let's look at this. What is the value of the reaction quotient before the reaction occurs? Okay, so if I'm talking about before the reaction occurs, I am indeed talking about calculating which letter? Q. We only calculate K when we're at equilibrium. So what is the Q expression for this reaction? And am I talking about pressures or concentrations here? I'm talking about concentrations. Okay, so I'm going to be using the brackets. Product over reactant squared. Very good, squared. Okay, so initially, before the reaction happens, how much reactant do I have? What's the concentration of my reactant?
2.1.
Okay, remember, this was a pretty simple one because it told you you only have 1 liter of solution. You only have a 1 liter flask, okay? Moles per liter, 0.1 molar, right? So that's the concentration that you would use. What if you had a different volume here that was not 1? Do you still have to divide these two to get the molarity to put into this? Yes, this is only molarities, guys. So that's the number that goes there, right? And what would you be doing to this number, 0.1? You would be, okay. Hey, but you guys, guess what? I mean, yes, this is all true, but how much product do you have before the reaction starts? How much product is there before the reaction starts?
None.
0. Before the reaction starts, guess what the Q value always is? 0. Okay. Is it always 0? No. At any other moment in time, it's not 0. But before the reaction begins, it's 0 because you haven't made any product yet. Haha, tricky, Miss Poe. Let's talk about units. That was one of the things that was on that slide that I forgot to mention. Let's talk about units of Q and K. Guess what? You guys are going to love this. No units. We don't write any units with these values. We don't write units with these. They are written as unitless values. No units. Hooray. What's the value of K? Same reaction, same problem. What's the value of K? Let's see what information we have in the problem. What do we have to calculate K? The concentrations at equilibrium. The problem is going to have to tell you, here are the equilibrium concentrations, okay? Or as we'll see later, we might have to figure those out for ourselves, doing some more math. But for now, problem is telling you, here's what it is at equilibrium. That's what we use. Okay, this is my format, right, of my K. Same as what we wrote for Q. What is the equilibrium concentration of our product as told to us in the reaction? We are told the product is 0.042. And the reactant at equilibrium is 0.016. And we need to do what to that number? Square it. And how many sig figs should this answer round to have? 2. So I got 160. Okay. Let me come back now to that slide. I said I need to go over a few of these things on this slide. And then we're going to look at 3. Okay. What do we know about K? I say K is a what? Constant. Doesn't change for a reaction. Unless you change the temperature. Okay, if you change the temperature at which you run a reaction, guess what's going to change? Your K, everything. Everything's rate, K value, everything's going to change. Okay, temperature dependent. So K is a constant, but it is temperature dependent. Okay. We already said, remember, Q and K have no units written with them. This phrase, the magnitude, okay, the magnitude indicates the extent. Let's think about what that means. If you have a very, wait a minute, sorry. I'm not even going to say this, but hang on a second. Guys, will you ever have a negative Q or K value? How come? How come? Do we ever have negative concentrations? Do we ever have negative pressures? You'll never have a negative value. Okay, never. Okay. How big this is tells you what about the reaction? Let's think. Look at the reaction we just did. The N2O, wait a minute, which way did we write this one? 2 N, okay, we wrote it that way. Okay. If our K is a very big number, this is pretty big. We're going to see some absolute monsters of numbers. Okay, this is pretty big. If this is a pretty big number, what does it mean there's more of at equilibrium? Which one has the higher concentration at equilibrium? Think about how division works. If this is a large number, it means the number on top is a large number, right? The number on top is always our product. This is a large number. It means the reaction is going mostly which direction? Towards the products, forward. Large. It's break time. Large K values mean what? What do we want to say? Mostly product at equilibrium. What's considered a large K value? I don't really have a good hard and fast place to draw the line. 100 or bigger. Okay. What if you have a small K value? What does that mean? It's mostly reactants still at equilibrium. Small number here means mostly reactants still at equilibrium. What's a small number? Less than 1. Let's say less than 1. What if your K value is right around 1? What does that mean? What would that mean? If you're getting a value of 1 when you divide, what does that mean? Approximately equal concentrations. I said that that's not what defines equilibrium, which is correct. Does that mean that they can't both be around the same? Sure they can, right? They can. Yeah. Approximately 1 means approximately equal concentrations of products and reactants. Okay, good. So look at 3. Here's the reaction. It's that same SO2 reaction that we looked at a minute ago. Here's some concentrations at equilibrium. I'm listing some values for you. What is K? Calculate K. You do not have to do Q before K. We're about to do an example where you should calculate Q, but it'll be apparent in the wording of the problem. See if this is what you guys get when you solve for K of that reaction on 3. And then we might go ahead and take a break. You need to be sure that you are squaring what needs to be squared, or cubing, or whatevering based on the coefficients. Yeah. Excuse me. And see if you guys get a value of 4.3. And you should now then be able to tell me what does that size value of K mean? Does it mean anything to you? This size number of 4.3 means the concentrations at equilibrium are pretty close to equal. That, of course, is taking into account their coefficients, right? You got to be thinking about what's the coefficient. I got to be squaring or cubing or whatever. But the effect of their concentrations is about equal. Okay? Both sides. Does this mean this reaction is slow? I don't know. Does it mean it's fast? Can K or Q tell us anything about the speed? What's the only K that can tell us about the rate? The rate constant, little k, right? That's the only thing that can tell us about rate. This K can't tell us about the rate at all, okay? Not at all. So I'm going to put this up. And I want you guys to jot that down, and this is what we're going to look at when we come back, is when we need to compare Q to the equilibrium constant. What do we say about equilibriums? They're dynamic, right? They're trying always to get to equilibrium. This is how we figure out how it's going to get to equilibrium. We're going to compare Q and our K value for a reaction. So these three statements, these three comparisons, and then when we come back, that's what we're going to look at, is making those comparisons. Okay? So go ahead and take a break. And we'll look at number 4 when we come back.